One second.
This meeting is being recorded.
Okay, welcome everybody to our seminar today. So, you're not seeing your screen anymore.
Yeah, one second.
This meeting is being recorded.
Okay, as I was saying, so it's time to start our seminar today. So we have Ajit from the Institute of Mathematical Science in India, who is going to talk about some aspects of fractional quantum Hall liquids. So please, Ajit.
Okay. So let me start off by thanking Francesco for inviting me, and I'm going to talk about very high energy collective states of partons in fractional quantum Hall fluids. This is work done in collaboration with Xiao Liu, who's at Zhejiang University, Andrei Gromov, who's at Brown, and Zlatko Papic, who is at University of Leeds. And the main reference is this work that appeared earlier this month. So I'd like to thank generous funding from the Science and Engineering Research Board in India, the Department of Science and Technology, and a coding package called Diagram, which we used extensively for our calculations. Okay, so the plan of the talk is as follows. I'm going to give a very quick introduction to integer and fractional quantum Hall effect. In particular, I'll focus on the fractional quantum Hall effect occurring in the lowest Landau level. And this will be described by something called the composite fermion theory, which I'll talk about. And then I'll come to the main part of the talk, which is this new collective mode that exists in certain fractional quantum Hall states in the lowest Landau level itself, and our explanation of what this mode is in terms of what are called partons, and then end with some conclusions and outlook. Okay, so let's start up with integer quantum Hall effect. So what is the integer quantum Hall effect? In the integer quantum Hall effect, what you do is you take a two-dimensional system of electrons and you place it in a strong perpendicular magnetic field, B in the Z direction, and you run the current one way and you measure the voltage the other way. So you measure Vxy over Ix. And what Klosch-von-Klitzing found was that the Hall resistance, which is the ratio of this voltage to current, is quantized in fundamental units of h over e squared. So what he found was this plateau at h over e squared. And the amazing thing about this quantization is that it's accurate to like about 1 part in a billion. And it does not depend on things like what is the sample type you use. So systems as different as gallium arsenide and graphene show the same phenomena. Then it does not depend on things like what kind of disorder you have, what is the exact geometric shape in which you make this sample, and so on. So it's a very robust quantity. And I think from last year, it's now forming the standard of resistance, which is called the Klitzing constant. So it's gone into our system of measurement. And this value Rk, which is h over e squared, is about 25,000 ohms. So what Klitzing found was that along with this quantization in the Hall resistance, the longitudinal resistivity is exponentially suppressed in temperature. So you get something like e to the minus delta over t, where delta is some gap in the system. Okay, so how do we understand the integer quantum Hall effect? The integer quantum Hall effect is somewhat easy to understand. So just like in the absence of a magnetic field, you get a Fermi sea of electrons. Once you turn on a strong perpendicular magnetic field, this Fermi sea splits into many degenerate levels called Landau levels. And the idea is that whenever you fill an integer number of these levels, you get a gap to excitations. Because let's say if I fill 3 Landau levels, then there is a cyclotron gap, which prevents me from going to the 4th Landau level. And one can also write down wave functions because these are simple non-interacting systems. So you can just write down slated determinant states. So for example, for the nu equal to 1 state, there's this famous Van der Monte kind of wave function that one gets by just filling the orbitals in the lowest Landau level. So here Z is a complex two-dimensional coordinate that parameterizes the electron coordinate. And then there is this Gaussian factor that you get characteristic of these Landau levels. Turns out that other than this nu equal to 1 state, we don't know any closed form wave functions for higher Landau levels. So numerically, one can construct these, but we don't know of any closed form wave functions for these higher Landau levels. So along with this non-interacting feature, the only additional thing that you need is Anderson localization, because you need a plateau. So what you need is the disorder to accommodate some of these states. Okay, but still this is a somewhat easier problem to understand because the essential physics is non-interacting. Okay, then very soon, just a couple of years after Klitzing's experiments, Sui, Stommer, and Gossard found something very remarkable. So what they did was they improved the sample quality, went to much higher magnetic fields, and did essentially the same experiment. Again, measured the Hall resistance and longitudinal resistance. And what they found was that phenomenologically, this looked very similar to the integer quantum Hall effect, except for now that the resistance was quantized in fractional units. So you get numbers which is like h over 1/3 e squared. The longitudinal resistance still vanishes, which again indicates that there is a gap to excitations in the system. So Sui seems to have remarked that he found quarks in a solid state system, but then a mere measurement of the energy scales would tell you that quarks are not relevant here. So all of this is like a milli-electron volt phenomena, whereas quarks come at mega-electron volt and higher. So how do we actually understand the fractional quantum Hall effect? Turns out that the fractional quantum Hall effect is a very difficult problem to understand because it arises solely from interactions. So for a theorist like me, a nice limit to study the fractional quantum Hall phenomena is to take this limit where you send the cyclotron frequency to infinity, or you send the electron mass to infinity, so that the gap between the lowest Landau level and higher Landau levels is infinitely large. Then the problem is kind of easy to state because then there is no kinetic energy in the problem. You just have electrons interacting via Coulomb forces. So the Hamiltonian is kind of simple to write down. It's just E square over epsilon r, that's all. Quantum mechanics in this problem is built in this fact that now you have to like project the states, project all the quantities to the lowest Landau level. So once you project to the lowest Landau level, these coordinates don't commute with each other. And what happens amazingly is that from this highly degenerate manifolds, for example, if you have 4 electrons in 10 orbitals, which corresponds to filling factor 2/5. So the filling factor is this number which tells you what are the number of electrons divided by the number of states in the system. So if you have 4 electrons in 10 orbitals, then the number of states that you can get is something like 10 choose 4. And if you take the thermodynamic limit, this number blows up very quickly. So somehow, amazingly, interactions pick out one unique states from this highly degenerate manifold. So one place that this should be contrasted from is like superconductors. In superconductors also, we have interactions playing an important role. But there, one nice thing is that if you switch off the interactions, then the state that you get is unique. You just get a Fermi liquid, and that we understand fairly well. But here, if you switch off the interactions, you just get a whole bunch of degenerate states. So in some sense, the fractional quantum Hall effect is like the most strongly correlated system in the world. Okay, so how do we make any progress at all? Like, we don't even know how to solve 3 particles interacting with each other. How are we going to solve like n, where n is very large, number of particles interacting with each other? So progress in this direction was first made by Laughlin, who essentially just guessed what the ground state wave function should be. So what Laughlin did was he assumed that electrons interact in this pairwise manner, which I call Jastrow form. And he assumed that every pair has this contribution, which is like Zi minus Ej. And then he also assumed that the states should be eigenstates of the angular momentum. And that actually fixes the form of the polynomial that you get in the lowest Landau level. So it's just some Zi minus Ej to the m. And then because this is a fermionic state, m has to be an odd integer, because of this form that when you swap 2 coordinates, then you should get a negative sign. Furthermore, Laughlin remarkably showed that this is a fluid which carries excitations which have a charge which is a fraction of that of the electrons. For example, if you look at filling factor 1/3, then the smallest charge quasi-particle that you can create has a charge which is E over 3. Okay, and then later on, Arovas, Wilczek, and Schrieffer showed that these particles are even more exotic in the sense that not just the charge, but their exchange statistics is also fractional. For example, if you exchange 2 particles, then they carry a phase which is like 2 pi by 3. So for example, if you just swap fermions, then you get a phase of pi. But for these particles, which are now called anyons, you get a phase which is also fractional. Okay, so this is the ground state and the charged excitations. But what about neutral excitations? So one way to think about neutral excitations is that they are composed of equal number of Laughlin quasi-particles and quasi. So that's one way to think about this. Another alternate picture that was given by GirvinMacDonald-Platzman, GMP, was that the neutral excitation, the lowest lying neutral excitation, is like a density wave. So it's like a collective mode of the entire fluid. So what they did was that they looked at the ground state wave function and suggested hitting it with the density operator. And because again, I would like to work in this limit where everything is in the lowest Landau level, I just project the state to the lowest Landau level. Or instead, what I can do is if I start with the state that lives in the lowest Landau level, I can project the operator to the lowest Landau level. So I take the density operator, construct its lowest Landau level version, and hit that on the ground state. And that gives me like a branch of excitations. So what they found was that they calculated the dispersion of this mode. So I get the 1/3 Laughlin ground state. And on top of that, I get a bunch of neutral excitations. So this neutral excitation exhibits a characteristic minimum, which is very similar to what you see in liquid helium. So there's this Roton minimum that one sees in liquid helium. And based on that, they termed this branch of excitations the magneto-Roton branch, because this is happening in a magnetic field and it has like a Roton minimum. So they call this branch of excitations magneto-Roton. And this name has stuck, and this will be like a crucial excitation for this, for what I'm going to say next. So very soon after 1/3, there was like a whole zoo of fractions which were observed. And these primarily fall along the n over 2p n plus minus 1 sequence. So 1/3 was the first fraction that was discovered. Then there was a state at filling factor 2/5, then states at 3/7, 4/9, etc. And in the lowest Landau level, you have the symmetry called particle-hole symmetry, where what I can do is I can exchange particle orbitals with hole orbitals. For example, if I have a state which is 1/3 filled, I could as well think of it as a state of 2/3 empty particles. So then by particle-hole conjugation, just for a state at 1/3, I can construct another state at 2/3. Then for 2/5, I can construct a state at 3/5 and so on. So at any filling factor nu, if I have a state, then by particle-hole conjugation, I can construct a state at filling factor 1 minus nu. So it's sufficient to just consider states at filling factor which are less than half. But then how do we go about understanding these states at filling factor 2/5, 3/7, and 4/9? One issue is that you can't simply go and put m as 5/2 or 7/3 in this Laughlin ansatz, because then this wave function is not single valued anymore. So it's not clear how one goes about constructing these states. Furthermore, it was actually noticed that phenomenologically, the integer and fractional quantum Hall effect are not fundamentally different. Like you still get a quantized Hall resistance and you get a vanishing longitudinal resistance. So maybe it's possible to understand the fractional phenomena as integer phenomena of some emergent fermions. And indeed, this assertion turns out to be true. The fractional quantum Hall effect can be understood as the integer quantum Hall effect of certain emergent topological objects called composite fermions, which are bound states of an electron and an even number of vortices. So you need an even number of vortices to maintain fermionic symmetry. So this will become clear in a couple of slides. And in many cases, vortex can also be viewed as a flux quanta, because when you like swap two particles, you get a phase because of the vortex, and that could also be viewed as some Berry phase in a magnetic field. So you're also welcome to think of the composite fermion as being made of an electron and an even number of flux quanta. So in this schematic, I chart out the golden path to go from the integer quantum Hall effect to fractional quantum Hall effect. You first start with electrons in a small magnetic field. Then what you do is that you bind to each electron two vortices or two flux quanta to convert them into composite fermions, which I show in this green schematic. And then you do this thing of like slowly smearing away the flux from the composite fermions to the external magnetic field. And in this process, you kind of hope and pray that the gap does not close, because this is a system that we are interested in. We are interested in a system of electrons in a large magnetic field. And we would like to describe it in terms of electrons in some smaller magnetic field. So there is one has to check whether this assumption holds or not. So it turns out for certain interactions, this will work out well. And for certain other interactions, this won't. And for these interactions where this assumption does not work out well, you need other theories to describe fractional quantum Hall effect. But throughout this talk, we'll be only concerned with states, with systems where this assumption works out well. And I'll demonstrate how well this assumption holds. So now what we can do is to run the tape backwards. So you start with electrons in a very large magnetic field. And then from this external magnetic field, you take two flux quanta and bind it to each of the electrons. So then what you get is you get a system of composite fermions in a lower magnetic field. And to the zeroth order approximation, what you can do is you just assume that the composite fermions are non-interacting. And just like non-interacting electrons in some magnetic field form Landau levels, composite fermions in this reduced magnetic field form their own Landau levels. So these are sometimes called lambda levels. And you get fractional quantum Hall effect whenever an integer number of these levels are filled. Okay, and this picture actually allows you to relate quantities of composite fermions with the quantities of electrons. So all start quantities are quantities for composite fermions, and unstart quantities are quantities for electrons. For example, B star is the effective magnetic field that the composite fermion sees. So that's the total magnetic field minus 2p flux quanta. Flux quanta is this hc over E. It's a fundamental unit of flux times the density. So what I do is for every electron, I bind two flux quanta. So that reduces the magnetic field that the composite fermion sees. And because the filling factor is related to the density and the magnetic field as follows, the filling factor of composite fermions is related to its effective magnetic field. And every electron forms a composite fermion. So density of composite fermions is the same as the density of electrons, but they see a different effective magnetic field. So that allows you to relate nu with nu star. And whenever nu star is n, where n is number of fill lambda levels, then you get an incompressible state at filling factor, which is n over 2p n plus minus 1. So this again explains why it is the case that in the lowest Landau level, you predominantly get fractions of this form, which are n over 2p n plus minus 1. So in particular, the thing to note is that this denominator is always odd. So these fractions are called the Jain fractions, and they describe majority of the fractions that are observed in experiments. So now let me just pictorially depict what the analogy between integer quantum Hall effect and fractional quantum Hall effect for ground state. So when you have one fill lambda level of composite fermions, then you get the 1/3 state of electrons. And it turns out that this state was exactly the state that Laughlin described. So I'll show why it is exactly the state that Laughlin described in a couple of slides from now. So this state was kind of already known. Now, if I look at 2 fill lambda level state, then that state corresponds to 2/5 filling of composite, 2/5 filling of electrons. Then 3 fill lambda level state of composite fermions corresponds to 3 fill lambda level state of 3 fill lambda level state of composite fermions corresponds to 3/7 state of electrons. So now, once you have this mapping, you can construct any state of FQHE by just appealing to this analogy to IQHE. For example, one can now also go ahead and construct excitations. So the simplest excitation that one can think of is like a hole in a system. So what you do is you just remove one electron from a given lambda level. So that under this mapping goes to a missing composite fermion from an otherwise filled lambda level. So this excitation is called a composite fermion hole. Then the particle excitation would be to add an additional electron in an otherwise empty lambda level. That in terms of composite fermion becomes like an additional composite fermion in an otherwise empty lambda level. Then a neutral excitation in this picture can be constructed by creating particle hole pairs. So that is what I call an exciton in the electronic picture. And in terms of composite fermions, it just becomes a composite fermion exciton. You create a pair of composite fermion particle and composite fermion hole. Okay, now this analogy also allows you to do something quantitative. And this quantitative stuff goes through via these construction of the wave functions, which are called the Jain wave functions. And the way you build them is as follows. So what you do is you first construct a slated determinant state of n fill lambda levels. So this state we know how to construct because this is just a slated determinant state. It's just a non-interacting state. You just occupy all orbitals. Then to this state, you multiply by this Laughlin-Jastrow factor of Zi minus Zj to the 2p. So then what happens is that every electron sees 2p zeros at every other electron. So this is this flux or vortex binding that you do. And then because I would like to work in this limit where I send the cyclotron frequency to infinity, I would like to project the state to the lowest lambda level. So what I do is I just brute force project the state to the lowest lambda level. So PLL is this operator which implements projection to the lowest lambda level. Now, if you look at phi1 is the same state as product I less than j, Zi minus Ej. It's just the van der Waals state. And that one can now see is identical to the Laughlin state because when you have just a holomorphic wave function, then you don't need projection because the holomorphic state automatically lives in the lowest lambda level. So if you set n equal to 1, then you get 1/3 with p equals to 1. And that is just Zi minus Ej to the power 3. Exactly the same state as Laughlin. So that's why 1 fill lambda level of composite fermions is exactly the same as the Laughlin state. The amazing thing about this wave function is that it's a variational wave function, but it does not have any variational parameter. So for example, if I fix the filling factor on the left-hand side, then everything else on the right-hand side gets completely fixed. So it's like a trial wave function, but it does not have any adjustable parameters. And one nice feature of this wave function which will be useful to us later on is that this wave function can be evaluated for very large system sizes. So that's not at all obvious, right? Because if you construct a state and you have to keep some part in the lowest lambda level, then the only way we usually know of is to like expand the state in the full basis of lowest lambda level, second lambda level, third lambda level, and just retain the part in the lowest lambda level. But this issue can actually be circumvented. There is a way to directly construct the projected state in the lowest lambda level. That's slightly technical, and I'm not going to explain how that one does that, but this is something that would be useful for us. The nice feature of these wave functions is that they can be evaluated for a very large system size. So maybe already some of you may have noticed that at the simplest fraction, filling factor 1/2, we don't get any fractional quantum Hall effect. We don't get any plateau, and we don't get any vanishing longitudinal resistance. So why is it that at the simplest possible fraction, one does not get any FQHE? So this again can be understood using the composite fermion theory. It turns out that in this process of binding flux to the electrons to turn them into composite fermions, you actually end up absorbing the entire external magnetic field. So the residual magnetic field that the composite fermions see is 0, is exactly 0. And just like electrons in zero magnetic field, composite fermions also in zero magnetic field form a Fermi C. So because a Fermi C is a gapless state, you don't get a gap state, which can then result in FQHE. But once you just step back a little bit and think about this carefully, so in the garden variety vanilla Fermi C that we are used to, that we study in solid state systems, the kinetic energy is the central part. and interactions are kind of not so important. But here, just from interactions alone, a Fermi sea is emerging. And this Fermi sea in particular is relevant for the exotic enigmatic states seen at filling factor phi-half. For example, there is a fractional quantum Hall state observed at filling factor phi-half at 1/2 in the second Landau level. And that's believed to arise from like a superconducting instability of this Fermi sea. Okay, so I said these things about Jain wave functions and composite fermion theory and so on. And one can ask, how good are these wave functions? Like, how accurately do they describe the problem of our interest, namely Coulomb electrons interacting via Coulomb interactions? So there are lots of geometries that one can choose to describe, do exact diagonalization for small systems and then compare against these variational wave functions. So I'm going to pick the spherical geometry. There are some nice features of the spherical geometry. One is that it's a compact geometry. So if you look at electrons in the planar geometry, then you have to like put a confining potential to keep them within some way, because otherwise they're just repelling each other and they'll just fly off to infinity. So on the sphere, there is no issue of this kind because it's a compact geometry. There are also other compact geometries one can use, like torus and so on. But in torus, what you would find is that these ground states are multiply degenerate. Whereas in the sphere, because it does not have any genus, there is a unique state that you get. So that's why I've chosen the spherical geometry. So for the spherical geometry, you have this unenviable task of getting a magnetic monopole from outer space and putting it at the center of the sphere to generate a radial magnetic field. So for theorists, this can be done easily. So what you do is you take the two-dimensional plane of electrons and wrap it around on the surface of a sphere. And this radial magnetic field is generated by a monopole which sits at the center of the sphere. And appropriate to this geometry, the orbital angular momentum and its z component are good quantum numbers. So it turns out that on the sphere, the relation between the flux quanta, number of particles, and filling factor is offset. So it's offset by some quantity called the shift. So in the planar geometry, the filling factor is just defined as the number of particles divided by the number of flux quanta. But in the spherical geometry, there is an offset. And this offset comes about because of coupling to curvature. And it's a very useful quantity which helps characterize the state. So what you can have is you can have different states which occur at the same filling factor, but they have different shifts. So this shift is also believed to be like a topological quantum number which can tell two states apart. Okay, so then we also need a way to parameterize the interaction. So what we do is that this was again done by Duncan Haldane. So what he showed was that if you take two electrons and place them in one Landau level, in any given Landau level, let's say lowest, first, whatever, whichever Landau level you want to pick, then you can parameterize any two-body interactions by just two particle energies. So for example, I just take two electrons, put them in relative angular momentum m state in the lowest Landau level and ask what is the energy cost for this. So this decays in this characteristic fashion. As you go far away, there's a lower cost because of this Coulomb repulsion, which decays in this 1/r fashion. And throughout this talk, I'm going to assume that electrons have only one component. So they are fully polarized. So only the odd pseudopotentials are relevant. So in general, both the even and odd pseudopotentials could be relevant. But because of this assumption that I make that we consider only fully polarized electrons, only the odd pseudopotentials are relevant. Okay, this completely specifies the problem. So you just tell what are the pseudopotentials and give the number of particles in flux quanta. Then for small systems, one can just brute force exact diagonalize the problems. For example, for 1/3, we can diagonalize the system up to 15 particles, which has a Hilbert space of about 2 billion. So one can ask, how good are these wave functions? So what is the overlap between the exact Coulomb ground state and this candidate ground state, which is like Laughlin state or the Jain state? So at filling factor 1/3, the Laughlin state has an overlap of about 99%. So it's like nearly exact. If you take a random state which has a Hilbert space dimension of this much, you would essentially get zero overlap. But this captures like almost 99% of the state exactly. And similarly for 1/5, again, you get a state which has an overlap of about 95%. Then for 2/5, 3/7, 2/9, these are the Jain states. You again get like almost unit overlap with the exact Coulomb ground state. So indeed, the ground states are very well captured by the ansatz that Jain and Laughlin proposed. Okay, now what about excitations? So we already know that the ground states are very accurate. How about excitation? So for at filling factor 1/3, this ground state is just the one fill Landau level Laughlin state. The branch of excitations, the neutral excitations, are composed of particle hole pair of composite fermions. Okay, and these again capture the exact ground states, very exact excitations very accurately. For example, this dot is the energy that you get by taking the composite fermion exciton, and this red dash is the energy that you get from exact diagonalization. And the amazing thing is that this dot captures like a linear superposition of about 2 million states, and it captures it almost exactly. And an important feature to note is that if you look at this branch of neutral excitations, then in the long wavelength limit, so the long wavelength limit is like the small angular momentum limit, it actually goes into the continuum. It goes and merges into the continuum. So it's usually not so easy to pick out these excitations, but at least at large angular momentum and large momentum, one can see that these excitations match really well with the exact ground state. Okay, so we gave actually two recipes to construct the neutral excitation. So one was this GMP ansatz, where you take the lowest Landau level projected density operator and act it on the Laughlin state, versus this composite fermion exciton ansatz. So these are two different ansatz. One can ask which one is accurate or how well do these match. So it turns out that generically the composite fermion exciton is much more accurate than the GMP mode. So in particular, if you look at the composite fermion exciton, it actually saturates in the long wave number limit. So you go to large angular momenta, then the dispersion flattens out. Whereas if you look at the GMP mode, the dispersion keeps going up as a function of momentum. So it just goes in this quadratic Q square form. So at least in the long wave number limit, it's clear that the CF exciton is much more accurate. But even in the small wave number limit, in general, the composite fermion exciton is much better. It gives a much better description of the exact ground state compared to the GMP construction. It turns out that for the Laughlin-like states, one can show that if you look at the long wavelength limit, then the composite fermion exciton and the GMP mode are exactly identical. But generically, for other fractions, the composite fermion exciton is much better than the GMP mode. Okay, so the CF theory gives a very accurate description of not just the lowest lying branch. So for example, if you look at other filling factors like 2/5, 3/7, and so on, it turns out that this neutral excitation, this lowest branch of neutral excitation, is well separated from the continuum. So there's like nice way for us to identify these states. So there's this first branch of excitations, and there is a second branch of excitations, and then there's third branch of excitations, and so on. And these are all very well captured by the composite fermion theory. So the dashes and dots can essentially not be told apart. And the dots are like a linear combination of about 1 million states. And all these states are like nearly perfectly captured by the composite fermion theory. So the composite fermion theory is like well established and extremely accurate in the lowest Landau level. Okay, so this is all the background that I needed to give for the main part of the talk. So let me just stop and see if there are any burning questions, or should I move ahead? Are there any questions?
Yeah, I have one. So do you mean that this composite Fermi description doesn't work for even denominators in the filling fraction?
Yes. So these even denominator states are not captured by non-interacting composite fermions. So if you assume that composite fermions are non-interacting, then you only end up with these odd denominator states. Just because of this feature that if you look at these wave functions, they occur at this n over 2p and plus minus 1. So if you take n and p as integers, then you can only get odd denominators.
I see. Thanks.
But you can describe even denominator states as interacting states of composite fermions. For example, paired state of composite fermions can capture an even denominator state. That's what this superconducting pairing does for you. And that state occurs at filling factor 1/2, which is our even denominator. Okay, so if there are no more questions, I would proceed. So the fractional quantum Hall effect has now been known for has been studied for like 4 decades. So what's like new or what's interesting about it? So very recently there was a puzzle that was found out in these composite fermion states themselves. So what was shown in effective field theory descriptions is that if you consider the secondary Jain states, so what I mean by secondary Jain states is if you look at fractions of the form n over 4 and plus minus 1. So for these n over 2p and n over 2p, this p equal to 1 is like the primary states, p equal to 2 gives you the secondary states. So for example, 1/3, 2/5, 3/7, 4/9, these are the primary Jain sequence. Then similarly, you have the second set of sequence, which is like 1/5, 2/9, 3 over 13, and so on. These are called the secondary Jain states. So what was shown by others, in particular Goldman and Fratkin, and also by Schoen and collaborators, was that if you look at composite fermion field theories, then for the secondary Jain states, they violate something called as the Haldane bound. So these Haldane bound, it places the lower bound on the coefficient of q to the 4 in the static structure factor. The static structure factor is the density correlated. So you take the projected density operator and you take its correlator, and this gives you the static structure factor. And what they found was that if you just describe them using standard effective field theories, then they actually violate this Haldane bound. So Nguyen and Schoen proposed a way to rectify this bound. They said that in addition to the GMP mode, there are additional higher energy collective modes, which if taken into account, that does not violate the bound anymore. But their proposal was kind of ad hoc. Like they just said that you take some modes and if you include these modes, then that fixes the bound. So what we did in this work that I'm going to talk about is to actually give a microscopic justification and construct a trial wave function to capture this additional mode. So the surprising thing is that this mode is not there in the primary Jain states. So it's only there in the secondary Jain states. And in particular, it's not there in Laughlin states. It's only there in states of the form 2/9, 3/13, and so on. Only in the Jain states and in the secondary Jain states. So all of this will become clear. So firstly, one can ask, what is the evidence for this additional mode? So one way to look for this additional mode is to calculate the dynamical structure factor, which is the response of the density operator. So you calculate the spectral function corresponding to the lowest lambda level projected density operator. So here En is the exact eigenstate. It's the nth eigenstate, and it has energy En. E0 is the energy of the ground state. And E is just this energy that you use to characterize the dynamical structure factor. So if you plot the dynamical structure factor as a function of the momentum and the energy, then what you find is this nice GMP-like mode, or the CF exciton mode. But additionally, you also see some weight high up. So as Nguyen and Schoen said, there is like a higher energy mode high up. And we do see some signatures of it in the dynamical structure factor. So that's one evidence that there exists this mode at filling factor 2/7. So for example, if you plot a similar dynamical structure factor at filling factor like 1/3 or 2/5 and so on, you won't see any signs of this high energy mode. Okay, in parallel work, Zhao, Andre, and Zlatko actually showed that if you do quench dynamics in this system, so for example, what you can do is you take this system and you introduce anisotropy in the system suddenly. So this anisotropy can be introduced by, let's say, straining the sample or tilting the direction of the magnetic field, which then changes the orbits. Then what happens is that actually couples to this long wavelength limit of the GMP mode. So in some sense, this introducing anisotropy in the system allows you to excite this collective mode. So what we did was we looked at this filling factor 2/7, and we did this change in anisotropy, and we looked at what is the response of the system. You measure fidelity and see at what frequencies do you get response. So what we find is that there is a response at some small energies, and this energy corresponds to the GMP mode. But there's a much bigger response at energies which are much higher, so in this ballpark. And this energy is roughly consistent with the energy that we see for the parton mode in this dynamical structure factor. Similarly, if you actually do this sort of calculation at filling factor 1/3 or 2/5 and so on, you just get a unimodal response. You don't get two frequencies, or you don't get two peaks in the spectral function. Okay, so how do we go about understanding this state? So one way to do this is by something called as a parton construction. So what Jain did was he actually generalized the composite fermion construction into a larger class of states, which are called parton states. And the way this construction goes is as follows. So what you do is you take the electron, you break it into fictitious subparticles called partons. And then you can place the partons into integer quantum Hall effect, or in particular, you can place them into any quantum Hall effect states, or in any known fermionic states. And you fuse the partons back together to recover the electron. So that gives you wave functions of this kind. So what you do is you take product of some phi n states. And again, because I would like to work in this limit where the magnetic field is sent to infinity, everything resides in the lowest lambda level, I just brute force project the state to the lowest lambda level. Now, a nice feature is that the state describes fermions, so the number of partons has to be odd. So that's one constraint that you get. Then because all the partons have the same density as that of the electrons, and they are also exposed to the same magnetic field as that of the electrons, that tells you what is the charge of the parton. The charge of the parton is related to the charge of the electron by this relation. Because they are at a different filling factor, the charge of each of the partons is different. And because you have this constraint that the sum of the parton charges should add to that of the electron, that actually allows you to relate the filling factor of the electron to the filling factor of the parton. So that's this central relation. Then one can also get the shift of the state on the sphere from this relation. So that would be super important. So in particular, the Laughlin state is a parton state in which you have 3 partons, each of them fill 1 Landau level. So it's a 1-1-1 parton state. This is probably the simplest way to see why the Laughlin state carries E over 3 particles. Because let's say if I want to set, I set nu equal to 1/3 and I set n equal to 1, then I get q, which is 1/3. So the Laughlin state is made up of 3 partons, each carrying charge E over 3. That's because of this thing that the 1 Landau level state is exactly the Jastrow factor. Then the Jain composite fermion states are also parton states. So they are n-1-1 parton states. So you get 2p plus 1 partons in general, where 2p partons fill nu equal to 1 Landau level and 1 parton fills n Landau. Okay, so with this one can actually understand what this additional mode is in these secondary Jain states. So one thing that one can do is to actually factorize the secondary Jain states into a product of primary Jain state and a parton state. So let me tell you how this goes about. So the secondary Jain state wave function is this phi1 to the power 2p times phi plus minus n. So what I do is I do the projection in this way. What I do is I take 2p minus 1, 2 times p minus 1 factors of phi1 outside. So that's the factor kept here. So this is a standard bosonic Laughlin state. And I just project the rest of the part. Because this factor already resides in the lowest Landau level, I don't need to project it. So I can just move it out and then just project phi1 square times phi plus minus n. So this then results in a primary Jain state. So one way to factorize the secondary Jain state is to write it as a product of a primary Jain state times a bosonic Laughlin state. So one can ask how good is this, how valid is this factorization? So I'll show that it is very accurate in a couple of slides from now. But once you do this factorization, this other mode is like immediately obvious. So the low energy mode comes from this fact that you have the primary Jain state. So the primary Jain state has this factor of phi n. So as we saw here, this phi n gives you the smallest charge parton. So for example, if you look at filling factor 2/5, 2/5 is made up of 3 partons. There are 2 partons which carry charge 2/5. So these are the partons which correspond to 1 Landau level. And then there is 1 parton which carries charge E/5, which corresponds to 2 Landau level. So if you create excitations in this phi n state, then those excitations are lower in charge. And therefore, because there is Coulomb energy, then you would expect these excitations to have lower energy. So the low energy mode comes from these primary Jain excitations of the primary state. So you can construct a composite fermion exciton in the primary Jain state itself. And the high energy mode comes from exciting this Laughlin state. So you take the bosonic Laughlin state and you construct an exciton in that. And that gives you this higher energy mode. Okay. So there are like 2 modes, one in which I create the exciton in the primary Jain state and the other in which I create the exciton in the Laughlin state. So one can ask, how good is this factorization? So it turns out that this factorization barely changes anything. So for example, if you look at different ways of projecting the Jain state to the lowest Landau level and asking what are the overlaps between these 2 states. So we can do this calculation for only about 8 particles. And it turns out that the overlap between them is essentially unity. Another thing is that if you look at the Laughlin state, then the overlap is actually identically 1. Because of this fact that the Laughlin state already resides in the lowest Landau level, you don't need to do any projection to it. So for example, if I want to construct the Laughlin state at filling factor 1/3 or 1/5, I can view it as Laughlin state of filling factor 1/3 times a bosonic 1/2 Laughlin state. And this also works as shown from numerics for other general Jain states. Okay, now with these wave functions, we can again go ahead and look at what are the energies of the parton mode and the composite fermion exciton. And we look at these energies we just get a nice dispersion. Here I've plotted many system sizes. So they all collapse onto one energy. So the composite fermion exciton in this long wavelength limit goes to an energy which is like 0.05. And this is kind of identical to, very close to this energy that we saw in the dynamical structure factor. We saw an energy which is like 0.05 in the long wavelength limit. And in the long wavelength limit, this energy is like about 0.13 or something. That's for a finite system. So in the thermodynamic limit, we get an energy which is like 0.15. These trial wave functions give fairly accurate energies for these parton modes. So this is another evidence that this parton mode is the additional mode that was missing in these field theories. Another way to actually see that there are 2 different modes is there are actually 2 modes that one can construct which have different clustering properties. So in particular, this parton mode, if you bring 2 electrons close together at a distance with keeping their separation r, then this parton mode has vanishes as r to the 1. Whereas this other mode vanishes as the composite fermion exciton vanishes as r cube. That's because it's only the Laughlin state which when you bring two electrons close together in the Laughlin state, if you bring two electrons close together, then the Laughlin state vanishes as r to the power 2p plus 1. Because if you look at the 1 over 2p plus 1 Laughlin state, that goes as product I less than z I minus ej to the power 2p plus 1. So if you bring two electrons close together, that vanishes with a higher power than what is mandated by the Pauli principle. Whereas this other mode does not have, this parton mode does not have any Laughlin factor, so it just vanishes as r. So now what one can do is to construct appropriate operators which have these characteristic pseudopotentials. So you take two-body interactions which picks out pseudopotential m equal to 1 or m equal to 3 or m equal to 5. And one can construct these operators and look at their spectral functions or response functions. And we find exactly what we kind of anticipate. So this low energy composite fermion exciton mode, it picks up weight in this r cube factor because it vanishes as r to the 3. So in the relative angular momentum 3 pseudopotential, whereas the higher energy parton mode has weight in the relative angular momentum m equal to 1. And no other relative angular moment are seen because these are the only two modes that are there. Okay, one thing that I haven't mentioned here is that one can also show that these modes actually carry different chiralities. And one has to define chirality in some particular way. But one simple way to see that is that in the parton mode, the exciton is hosted by the Laughlin state. So the Laughlin state actually sees effective magnetic field in the same direction as the external magnetic field. Whereas in this other exciton mode at filling factor 2/7 in particular, this state sees a magnetic field in the opposite direction because this 2/3 is like the particle hole conjugate of 1/3. So because of this whole conjugation, the direction of the chirality is switched around. So one can in particular show that these two states carry different chiralities. Okay, so one question that still needs to be answered and which we haven't understood really well is that why is this mode absent in primary Jain states? So one thing we know is that numerics clearly show that this mode is not there. So for example, if you just do things like structure factor or quench dynamics and so on, we just get a unimodal response and we also get weight in only one. So one thing one can readily see is that the Laughlin fractions cannot support any other mode because the Laughlin state is made up of only one kind of parton, where each parton fills one Landau level. So all you can do is to excite, create a particle hole pair in one of these factors. Okay, now with this in place, one clearly now knows that at 1/3 you expect to get only one mode. Now what you can do is to do particle hole conjugation. So now if you look at 1/3 and you do particle hole conjugation, then you go to 2/3. So if 1/3 has only one mode, then by particle hole conjugation, 2/3 can also have only one mode. Now because 2/3 is of this form, which is like phi2 star, like 2 Landau level complex conjugate times phi1 square, it's actually analogous to the 2/5 wave function, where the only thing that is different between 2/3 and 2/5 is that one of them has phi2, the other has phi2 star. So if phi2 star has only one mode, you'd expect that 2/5 also supports only one mode. And one can make this sort of cascading argument to show that none of the primary Jain states support this higher mode. So what we believe is that if you project the state into the lowest Landau level, then a wave function of this kind. So for example, what is the analogous parton wave function that one can write down? The idea would be to keep the phi n as it is and create an exciton in the phi1 state. Then what we believe is that if you project the state to the lowest Landau level, then projection somehow annihilates the state. And numerically, we haven't been able to show this yet because it's very difficult to technically like construct the state. But recently there appeared another paper on the archive which gave a different argument based on geometric fluctuations of conformal Hilbert spaces to show that there is indeed only one mode in these primary Jain states. So their essential argument was of this kind. Like if you look at modes of this kind in the primary Jain state, then they vanish in only one particular way, which is R. That's all. Okay, so I'm coming to the end of the talk. So let me just say that we've uncovered some very high energy excitations in the Jain states. And an interesting feature about these states is that they lie beyond the composite fermion theory. So usually if you talk about Jain states, they would be taken to be synonymous with composite fermion states. So all excitations are like excitations of composite fermions and so on. But we have managed to show that there are some excitations which lie beyond the purview of the composite fermion theory. But they are captured in terms of these partons. So one interesting question to ask is how do we actually probe these modes? Like what kind of experiment should one do to be able to capture these states? So one issue is that they are very high energy, so kind of lie in the continuum. So how do we like pick out these excitations? So that's not clear yet. How do we go about like experimentally accessing these modes? Another interesting question would be like, what is the nature of these modes for other exotic states, like these even denominator states that somebody asked about? In particular, if you look at like non-abelian states, then what kind of collective modes they host, and is there something interesting about these collective modes? Okay, so with that, let me just wrap up. So let me give you a one-line take-home message. Partons are like real quasiparticles of quantum Hall fluids, and just like quarks in QED, they become evident when you probe the system at very high energies. So in particular, you get two modes in these secondary Jain states. So there's this composite fermion exciton mode, and then there is an additional parton mode, which is like the excitation of this bosonic Laughlin state. Okay, with that, let me just thank you, and I'll be happy to take any questions.
Okay, thank you very much. So then it's time for questions. So if everybody has a question, please.
May I question?
Sure.
Yeah, I will ask about some premises of the model, because it seems to me that you are not aware that concept of composite fermion is, in view of modern experiment, a bit obsolete and inaccurate, at least because nowadays experimentalists observed circa 200 features of fractional quantum Hall effects, but composite fermions are able only explain at most 20 in the lowest Landau level. And so discrepancy in other situations is large and completely preclude usability of composite fermion model. And this idea of this fluxes pinned to electrons with a central in Jain model is artificial, because you know this fluxes on which field this field does not exist is only manifestation of another topological fact. And even if not discuss about conceptual premises, the wave function you also explicitly use is incorrect, because does not keep the symmetry. This projection into lowest Landau level spoils this wave function and is not fully correct. This is some situation that the Halperin multi-component wave function, the lowest level, the lowest Landau level, even better accommodate ground state energy for many fractions than composite fermions. So finally, I would like to ask what you can say about Chern topological fractional insulators, where also the fractional structure is similar in whole system, but without any magnetic field, certainly do not present the composite fermion. What is your opinion about it?
Yeah, let me just say. So I mean, firstly, there is the symmetry remains. There's no. It doesn't violate any symmetry. These wave functions. I mean, you could ignore this picture of like flux attachment and vortex binding, etc. But these wave functions are finally, at the end of the day, constructed for electrons. They are legitimate wave functions for electrons because they live in the right Hilbert space. They have all the right symmetries and so on. So it's not true that they violate any symmetries. It is indeed true that there are certain fractions. I wouldn't say like very few fractions in the lowest Landau level which are not captured by composite fermion theory. But they can also be understood using composite fermions if you allow for some interactions between composite fermions. So if you just take the non-interacting composite fermion theory, then it is well known that it is inadequate. It cannot explain all the fractions. There are certain delicate fractions which lie beyond the purview of non-interacting composite fermions. But if you allow for interactions, or you go to other theories like the parton theory and so on, one can capture almost all of these fractions. So in fractional Chern insulators, again, I don't know much about them, but the belief is that they are analogous to these fractional quantum Hall states. So they are just like lattice analogs of these continuum quantum Hall states. So this presence of a magnetic field is not particularly important, right? Like in this way that I wrote down, you just take the coordinates and construct vortex in the wave function. So you don't really need flux attachment as such. And in particular, Jain's construction is not about flux attachment. It's actually about vortex attachment. It's just because this Chern-Simons formulation of composite fermions, which allows you to write down effective field theories, that proceeds via flux attachment, that the two have now been like taken to be synonymous. But actually in this wave function construction, you don't talk about flux attachment at all. It's about vortex attachment. And that one can do with just the coordinates of the particles.
Well, finally, I would like to add that the claim that partons you introduced are quasiparticles, similar as composite fermions quasiparticles, is a bit risky because quasiparticles are a well-defined object. They need to be well-defined local order parameter in terms of mass operator, dressing of bare electrons with interaction. It's impossible to dress electrons in Coulomb interaction to dimensional space to produce magnetic flux. It is quite apparent, and therefore absolutely is impossible to use such terms as quasiparticles. These partons, similar as composite fermions, is only manifestation of multi-loop trajectories and commensurability property of cyclotron orbits in the case of planar geometry. And this is rather confusing to mixture local and global terms. Trajectories, multi-loop orbits, and so on are topological, but quasiparticles are local. And in this even some terminology is some confusion, isn't it?
I mean, I think one thing one can do is like forget about where the wave function is coming from. Let's say I just give you the final electronic wave function and I don't tell you where I constructed it from. Then one can ask how good is this wave function and how well does it describe things. And at least that there is no doubt that these wave functions are extremely accurate and they capture now both low and high energy properties of this thing. But other than that, where this wave function comes and so on, there are some pictures that one associates with these. That one may not take very seriously. Yeah, that's all I have to say.
Maybe I have one question.
Yeah. Okay. Finally, I would also advise to look at the paper about limits for application of composite fermion models. Some problems are detailedly explained to us. Thank you.
Okay, thanks.
So let me ask you this. So you mentioned that these states like resemble like fluids, and there is like this new proposal of Son, I guess, that says that these GMP modes can be understood as somehow like viscoelastic liquids. Could you, in principle, like test any of these properties, like transport properties, using your wave functions that you showed us?
I don't know about these viscoelastic properties, but I know of this proposal that this acts like a graviton, and then this has the spin-2 feature. That actually can be tested. So what you can do is to construct an operator which carries spin-2 and then look at its response. And one can see that that response fires exactly at the energy of these wave functions. So that we actually did in our paper, but I don't know about this viscoelastic response.
So yeah, that's, I think, an unpublished paper called Chiral metric hydrodynamics. I don't know if you saw it, but you can have a look.
No, I haven't. Okay, thanks. Yeah.
Thank you.
So any other question in the audience?
Maybe I'll ask the question.
Okay, please.
Can you give any physical justification for the deviation of the electron to the number of partons? Because you said that in some cases you divide it for 3 partons, in some cases for 5 partons. Can you give any physical justification when those division occurs, and on how many partons should it occur, and so on?
Yeah, so let me explain that. Do you still see my screen?
Yes.
Okay, so here, when I write down this wave function, then the only condition I have in mind is that the number of partons has to be odd, because what I do is I want to construct states which are known states, and I know only like fermionic states. So the only condition, at least at this point, is that the number of parton states should be odd. So you get like 3 partons or 5 partons and so on. Now, what one can do is actually combine some of these states. So, for example, in this way of when we went further down, right, we kind of view this secondary Jain state as being made up of 2 partons. So one is this primary Jain state, and one is the Laughlin state. So this number of partons is not really like a fundamental quantity. You can combine states of multiple partons together into one state and call that a parton state. So here it's just divided into 2 partons, but it turns out that both are not fermionic. So this parton state is a fermionic state, but this one is a bosonic state. So the number of partons is not really a fundamental quantity. You can always combine multiple states into. The only thing you have to keep sacred is that the final state should be antisymmetric. That's all.
But you have, for example, for the Laughlin state, you have to have 3 partons with everyone from the lowest Landau level. So
you have to have 3 partons if you insist on constructing integer quantum Hall state.
You have to have 3 partons for the Laughlin state, yes?
If you insist on constructing them from integer quantum Hall state.
Yes.
Right. Another way to view the 1/3 Laughlin state is a product of bosonic 1/2 Laughlin times phi 1. That's just 2 partons.
Thank you.
So usually what we do is we construct in terms of integer quantum Hall state. So then we need 3 partons. And the relation that relates the filling factor of the parton to that of the electron is this. So then if you put n equal to 1,
so there are no physical justifications when you should use what division?
No, there is nothing. There isn't.
Okay, thank you.
Yeah.
Okay, so it seems we don't have more questions. So if that's the case, so then I thank again Ajit for accepting giving the talk, and then with this we conclude.
Thanks for having me. See you, bye.